In computer science, search refers to the process of finding a specific item, record, or piece of information within a collection of data. The objective is to locate the desired element efficiently and determine its presence or absence. Searching is a fundamental operation in various algorithms and data structures, and it plays a crucial role in information retrieval, database querying, and problem solving across a wide range of applications. Different search algorithms, such as linear search, binary search, and hash-based search, are employed based on the nature of the data and the efficiency requirements of the task at hand. Search problems arise in many applications like information retrieval, database querying, sorting algorithms, pathfinding in graphs, AI, recommender systems, pattern matching, network routing, genetic algorithms, spelling error detection and correction, and game playing. In information retrieval, search problems arise in web search engines and document retrieval. Google, Bing, and other search engines use sophisticated algorithms to retrieve relevant information from the vast amount of data on the internet. Search is employed in databases and document repositories to locate specific files, articles, or information. In artificial intelligence, search problems arise in game playing and problems in planning and robotics. Search algorithms are essential in game playing, where they are used to explore possible moves and determine optimal strategies. In AI planning, search algorithms help find sequences of actions that lead to desired states. In robotics, search is crucial for path planning. In databases, search problems arise in query optimization and data mining. Search techniques are used to optimize queries in databases, enabling efficient retrieval of data. Search algorithms help discover patterns and trends in large datasets, supporting data mining applications. In natural language processing, NLP, search problems arise in text mining and information extraction applications. Search is used to extract relevant information, keywords, or patterns from large text corpora. NLP applications use search to locate and extract specific information from unstructured text. In computer networks, search problems are useful in routing algorithms and in network topology discovery. Search algorithms determine the best path for data packets to travel from source to destination, optimizing network traffic. Search techniques help discover and map the structure of computer networks. In computer vision, search is used in object recognition and image retrieval. Search is employed to locate and identify objects within images or video streams. Search algorithms also help find similar images based on content or features. Let us define a basic search problem. In a generic instance of such a problem, a table of records is considered. Each record comprises of attribute values, with one specific attribute designated as the search key. The objective, given a user-defined search key value X, is to locate a record with a key value precisely matching X. To simplify, in this lesson, we will assume that each record solely consists of the corresponding key value. Search problems in computer science may be classified into various types. Linear search. Linear search sequentially checks each element in a list, making it suitable for unordered datasets or small lists. Binary search. Binary search efficiently locates elements in a sorted list by repeatedly dividing the search space in half. Tree-based search. Tree-based search algorithms, like in binary search trees, organize data hierarchically, enabling faster search operations in sorted datasets. Hash-based search. Hash-based search utilizes hash functions to map keys to indices, providing constant time complexity for search operations in hash tables. Digital search. Digital search, often associated with tries or digital trees, organizes data by individual characters, facilitating efficient string-based searches and pattern matching. In this lesson, we will look at linear and binary search problems. Linear search is the simplest form of search wherein the key value is looked up by traversing through the sequence and examining one element at a time. For an unordered sequence, we compare each element to the user-provided key value, X, until an element equal to X is found or the end is reached. In case the sequence is ordered, we can take advantage of the ordering. In the case of a sequence ordered in non-decreasing order, the search can be terminated early if an element in the sequence is greater than X. In the case of a sequence ordered in non-increasing order, the search can be terminated early if an element in the sequence is less than X. Time complexity is order n. Let us assume an unordered sequence in the input. We iterate through the sequence. At each step, we compare the current element with the user-defined key X. If X matches the current element, the search is successful. If we reach the end of the sequence without finding a match, the search is unsuccessful. Overall, the algorithm takes order and time. Let us assume an ordered sequence in the input. In this case, the sequence is ordered in non-decreasing order. We iterate through the sequence. At each step, we compare the current element with the user-defined key X. If X matches the current element, the search is successful. If we reach the end of the sequence without finding a match, the search is unsuccessful. The search can be terminated early if an element in the sequence is greater than X. Overall, the algorithm takes order and time. Let us look at an example of linear search on a sequence sorted in non-decreasing order. To search for 14, we look at elements -17 at location 0, -1 at location 1 and then 13 at location 2. Then we find that 15 is greater than 14. Since the sequence is sorted in non-decreasing order, there is no hope of locating 14 beyond this point. So, the search terminates unsuccessfully. To search for 15, we look at elements -17 at location 0, -1 at location 1 and then 13 at location 2. Then we find 15 at location 3. So, the search terminates successfully. To search for 65, we scan the sequence from left to right. On reaching the end of the sequence, the search terminates unsuccessfully. Let us again assume an ordered sequence in the input. In this case, the sequence is ordered in non-increasing order. We iterate through the sequence. At each step, we compare the current element with the user-defined key X. If X matches the current element, the search is successful. If we reach the end of the sequence without finding a match, the search is unsuccessful. The search can be terminated early if an element in the sequence is less than X. Overall, the algorithm takes order and time. Let us look at the problem of linear searching in a sequence sorted in non-increasing order. To search for 4, we look at elements 17 at location 0 and 11 at location 1. Then we find that 3 is smaller than 4. Since the sequence is sorted in non-increasing order, there is no hope of locating 4 beyond this point. So, the search terminates unsuccessfully. To search for 1, we look at elements 17 at location 0, 11 at location 1 and then 3 at location 2. Then we find 1 at location 3. So, the search terminates successfully. To search for -64, we scan the sequence from left to right. On reaching the end of the sequence, the search terminates unsuccessfully. A more efficient algorithm exists for searching a key in an ordered sequence compared to linear search. This algorithm employs a systematic narrowing down of the potential index interval for the search. Initially, the algorithm compares the user-defined search key, X, with the middle element. If they match, the search concludes successfully, providing the index of the middle element. In case X is greater than the middle element, the lower half of the list is excluded from further consideration. Conversely, if X is smaller than the middle element, the upper half of the list is disregarded. As the interval size for the search is halved in each iteration, the algorithm either successfully concludes or reduces the interval size to 1. Consequently, the algorithm exhibits a time complexity of order log n, where n is the size of the input sequence. Note that binary search cannot operate on an unordered sequence. Shown here is an example of binary search. The key value being searched for is 38. The interval of interest is gradually refined by the algorithm. Starting with 0,15, it is reduced to 0,6, then to 4,6, and finally to 6,6, concluding successfully. Binary search can be applied to problem solving using neural networks. During the training of neural networks, finding an optimal learning rate is crucial. Binary search can be employed to efficiently search for the learning rate that converges the model most quickly and effectively. Appropriate weight initialization is essential for the convergence of neural networks. Binary search can be used to find the optimal range or distribution for initializing the weights of the neural network layers. Neural networks have various hyperparameters, and binary search can be used to optimize these hyperparameters efficiently. For instance, it can be applied to search for the optimal number of hidden layers or units in a layer. Here is a question. Suppose we have an unsorted sequence of n integers. The problem we need to solve is a search problem for a user-defined key value x. Should we use linear search or binary search? So here is the answer to our quiz question. Let us assume it takes order n time to linear search and order log n time to binary search. Binary search can operate on a sorted sequence only. Let us assume the sorting algorithm takes order n log n time. Since the sequence is unordered to start with, it may seem that binary search, with its sorting overhead, is automatically ruled out. But if you have k items to search, linear search takes order k times n time. Binary search would require order k times log n time along with an order n log n overhead. So if k is large, that is, we need to search several times, the overhead seems to be justified. This idea has wider applications in computer science. Often, we accept a pre-processing time overhead to speed up subsequent query times. A Google search is fast because of various pre-processing that has been done prior to even the query being asked. Thank you. This course is brought to you by Elahey Technologies.